Okay, good morning everyone. Today we are going to be looking at isotopy, calculation of relative abundances, calculation of relative atomic masses. What is isotopy? Isotopy is a phenomenon whereby atoms of the same element have the same atomic number but different mass number. Or you can say they have different number of neutrons. Okay, so it is possible scientists found out that an element can have different mass number but the same atomic number. Actually, atomic number, which means the number of proton, is used to identify an element. It's used to identify an element. So a particular element is identified using the atomic number. Now, you can see that some isotopes of elements are natural while others are created. Now, but before I go into this, I want us to look at these examples. Carbon-12 and carbon-13 are naturally occurring isotopes of carbon. If you notice here, they have the same atomic number, but different mass number. So, how do we know it is carbon? Both have the atomic number of 6. But mass number can differ. Mass number can be different. Okay? But artificially made carbon, which is carbon-14, I'm sure you know this that is used for radio dating and all of that. Okay, so naturally occurring carbon isotopes, carbon-12, carbon-13, but artificially occurring isotope is carbon-14. Now, another example here is oxygen. Oxygen have 3 isotopes. Oxygen have 3 isotopes. That means in nature, there are 3 isotopes of oxygen. We have the oxygen 16, we have oxygen 17, and we have oxygen 18, and so on and so forth. Now, I would like us to note something here, that most elements exist as isotope. Actually, it's very difficult to see an element that exists as just one atom. Most elements exist as isotopes. Remember what an isotope is? The phenomenon whereby an element or the atoms of an element have the same atomic number but different mass number, or you can say have the same atomic number but different number of neutrons. Now, I didn't write anything here, but we should also note that isotopy as a phenomenon is the reason why the relative atomic masses of elements are not whole numbers. I'm sure that is a very common question, especially down here. Isotopy is the reason why the relative atomic masses of elements are not whole number. And we are going to explain that. Okay, now we want to look at calculation of relative abundances. Now, what is relative abundance? Relative abundance is the percentage or ratio of naturally occurring isotope in the atmosphere. I want to use the example of carbon-12 and carbon-13. Naturally, in the atmosphere, carbon-12 is about, I may not be correct, is about 99% or maybe 98.9%. Okay, while carbon-13 is about 1.1%. So that the percentage of carbon-12 in the atmosphere is 98.9%, but the percentage of carbon-13 in the atmosphere is about 1.1%. Now, the same thing with oxygen. Each of these isotopes have their relative abundances. That means exist in a particular percentage, or we can say exist in a particular ratio. Okay, now let's come back here. Now, relative atomic mass. Now, relative atomic mass can be calculated using the sum of the average masses of the isotopes of an element using this formula. F1M1 plus F2M2 plus ... plus FMNN, depending on the number of isotopes that element is consisting of, and it is equal to the relative atomic mass. So scientists found out that the average mass, that the relative atomic mass can also be the average mass of the isotopes of that element. Now your F here represents the mass number of the isotope, and the M here represents the relative abundances. So if I'm given mass number of the isotope, which is F, and I'm given relative abundances, I can find the relative atomic mass using this formula: F1 M1 plus F2 M2 plus ... Fn Mn. Let's see an example here. What is the relative atomic mass of chlorine if it has two isotopes with the mass numbers 35 and 37? So chlorine has chlorine 35 and chlorine 37 with abundances of 75% and 25% respectively. Okay, and we also asked to calculate the same if given in ratio. So like I said, relative abundances can be in percentage and can also be in ratio. And you shouldn't be surprised with that, because when we say 75 ratio 25, dividing both sides by 25, which is a smaller percentage, is going to give us 3 ratio 1. So relative abundances can be given in percentage. It can also be given in ratio. But we are going to calculate the relative atomic mass now of chlorine using this. Okay, so we have relative atomic mass equal to F1 M1 plus F2 M2, since we have just two isotopes. Now F1 now talked about the mass number for the first one is 35 times the relative abundance is 75%. 75% means 75 over 100. Now plus F2 is for the second mass number, this mass number of the second isotope, which is 37. So 37 times M2 is the relative abundance for that. That is 25 over 100. 25 over 100. Okay. Now, if you use your calculator to check the whole of this, we are going to be getting that the relative atomic mass of chlorine is 35.5. Okay, I will see this as I. Now, but if we are given the ratios, we can find the relative atomic mass using the same formula. Relative atomic mass is equal to, but in this case now, we have 35 times the ratio here, 3 ratio 1. The ratio for this is 3, so we can say 3 over 4. How did I get 4? Meaning the total ratio. If their individual ratio 3 ratio 1, the total should be 3 plus 1, which is 4. So 3 over 4. Then plus 37 times 1 over 4. 1, because that's the ratio, then all over the total ratio 4. When you calculate this, we are still going to get the same value, which is 35.5. This is the reason why the relative atomic mass of chlorine is 35.5. Another way questions can be asked here is you can be asked to calculate the relative abundance of each of the elements. The atomic mass of naturally occurring neon is 20.18. Here we are given the atomic weight, which is relative atomic mass. Naturally occurring neon is composed of two isotopes, neon 20 and neon 22. So calculate their relative abundances. Here we have to calculate relative abundance. But remember our formula, the relative atomic mass is equal to F1 M1 plus F2 M2. Now, the relative atomic mass given here is 20.18, and it is equal to, now F1, the first mass number is 20. Now, we don't know the relative abundance, so we can call it X. Now plus F2. What is F2? F2, the second mass number is 22. If the relative abundance of the first is X, the relative abundance for the second, we can write it as 1 minus X. That's if we are calculating in terms of fraction. Now, we can say here that 20.18 is equal to 20x plus, I can open this bracket up, which will give me 22 minus 22x. I want to pause here to reiterate that if the relative abundance of one element, one of the isotope is X, the relative abundance of the next isotope will definitely be 1 minus X. Remember that the sum of fraction must be equal to 1, just like the sum of percentage must be equal to 100%. Okay, so we can come here and say, if we collect like terms, we are going to have that 20.18 minus 22 is equal to 20x minus 22x. We did that by collecting like terms. Plus 22 crosses the equal sign. That makes it minus 22. So already on the right hand side, we already have 20x and we have minus 22x. Okay, if we continue with that, this is going to give us minus 1.82 equal to, this is minus 2x. 20 minus 22 is minus 2, which to find x now we divide by minus 2. So we have here divide by minus 2, divide here by minus 2, and we are going to have that x is equal to 0.91. So that's to say that the relative abundance for the first isotope, which is neon 20, is 0.91. 0.91 also means 91% if you multiply by 100. How do I get percentage from fraction? Just multiply by 100. So the relative abundance for the other isotope, so this is for neon 20. Then for neon 22 now, the relative abundance will be 1 minus x, which means 1 minus 0.91, and that's going to give us 0.09. That's the fraction. 0.09 can also be written as 9%. How do you get 9%? You multiply 0.09, the fraction, by 100, you get 9%. Another way you can achieve 9% is by subtracting 91% from 100%. So if the relative abundance of neon 20 is 91%, it means that the relative abundance of neon 22 will be 100 minus 9%, which is 9%. Now let's look at question 3, but we'll be going a little higher here. Here, oxygen is composed of 3 isotopes: oxygen 16, oxygen 17, oxygen 18. Oxygen 17 has a relative abundance of 0.037%. Calculate the relative abundance of the other 2 isotopes if the average atomic masses of oxygen is 15.9994. Okay, in this case, we are going to have, now we already told that oxygen 17 has a relative abundance of 0.037%. And which means that the combination of oxygen 16 and oxygen 18 have a total relative abundance. Remember, we are only told the relative abundance for oxygen 17. We are not told for that of 16. We are not told for that of 18. It means that the total relative abundance for these two will be this 100 minus this particular value. Minus this. Remember, the total percentage must be equal to 100. Okay? So, if I subtract this value from 100, let me say 100 minus 0.037. That is going to give us 99.963, I guess. 99.963. Please, you can also confirm. Okay, so we can now say that relative atomic mass in this case here would be F1M1 plus F2M2 plus F3M3, because we have three different isotopes now, which is equal to, now the relative atomic mass given here is 15.9994, 15.9994. Now I would use this for oxygen 17. So this is the mass number, which is 17, times the relative abundance here is 0.037 divided by 100. Now plus, what is F2? F2 now we can use oxygen 16, which is 16 times, we don't know the relative abundance, so we can call it X. Then plus F3 is 18, that's the third mass number, 18. Then your M3 now in this case would be 99.963 minus X. 963 minus X. Of course, all together over 100, since we use over 100 here. Now, at this point, we need to expand to find X. So, your X now, after calculation,